What's up, guys? Today I'm doing a video on the characteristics of logarithm graphs. And so first we're going to start with the real basic one. F of x equals log x. It's kind of the basic logarithm graph. Okay, and I didn't even bother to label the y-axis in this case because I want to draw attention to the x-axis. Okay, notice that if I turn it sideways like this, that looks just like an exponential graph. Okay, and again, we talked about this in the other video. That's essentially what this is. It's the inverse of an exponential graph. So it has a lot of the same properties, but backwards. Okay, so whereas an exponential graph, goes left and right forever, and it has an asymptote that it approaches, which is usually the x-axis, unless it's been shifted up or down. Okay, well, this is going to have those same properties. In this case, instead of having a domain of all real numbers, it's going to have a range of all real numbers. It's going to go up and down forever. So the range is going to be all real numbers. And it's to the point that I'm actually not even going to write this anymore. From now on, just understand the range is always all real numbers. What's interesting is the domain and the asymptote and the intercepts. Okay. So the domain is going to be just like the range for exponential graphs. In an exponential graph, we used to try to figure out where that asymptote was, and then we'd say, well, the range was everything above that. Well, in this case, you find the asymptote, and you're going to say, well, the domain is everything to the right of that. Okay, the graph could be shifted left or shifted right, which would move that asymptote. In this case, the asymptote is the y-axis. So for the asymptote, I can say it's x equals 0, which is another way of saying the y-axis. The line x equals 0 right here is the asymptote. So the domain is going to be everything to the right of that. So the domain is where x is greater than 0. Notice I did not put equal to because this will not equal. It will never actually reach the axis. Which kind of brings me to another point. If it never reaches the axis, then you know that the y-intercept is none. It's never actually going to get there, so it can't have a y-intercept. It can't ever cross the y-axis. And the x-intercept, you can clearly see, is 1, 0. Okay, so for the next graph, let's consider a transformation. If I subtract here, you may recall from all the previous transformations and function types that we've studied, when you subtract inside of a function, which in this case means directly from the x inside the logarithm, that always shifts left and right. When you subtract, you go right. When you add, you go left. So I often say inside is left and right, and it's backwards. It's backwards from how you might think. Subtracting actually moves everything to the right. Adding moves everything to the left. So if everything moves to the right, then the asymptote goes from being at the axis, the y-axis, to going from x equals 0, shifting to the right 2 units to x equals 2. Okay, so our asymptote is actually x equals 2, which means our domain is everywhere that x is greater than 2. Okay. Another way of thinking about the asymptote is, what can I plug in that's going to make the inside of the logarithm 0? Because the inside of the logarithm can't be 0, that's why the graph approaches it but never actually gets there. So whatever makes the inside of the logarithm 0, that's going to be the asymptote. Okay, so in other words, if I were to set x minus 2 equal to 0, the answer would be 2, and that's why that is the asymptote. In the original problem, what's going to make the part inside the logarithm 0? Well, that's all there is. It's just x. So 0 would make it 0. Well, now that everything's shifted over, what else did that change? It changed the x-intercept. Notice now that instead of crossing at 1, it crosses at 3. Okay, and you can find that algebraically. If you didn't do the graph, how would you know that? How would you know that the x-intercept is 3? Okay, so what we can do, remember for the x-intercept, you can plug in a 0 for the other variable. So if I were to say 0 equals log x minus 2, I could solve this, and this would tell me the x-intercept is 3. How does that work out? Well, this is base 10, right? So I can rewrite this 10 to the 0 power equals x minus 2. Okay, remember rewriting, the base stays the same, the other parts switch. So the 0 becomes the exponent, and the x minus 2 goes to the other side. What is 10 to the 0? That's 1, right? Anything to the 0 is 1. So if I add 2 to both sides, I get 3. So 3 equals x. Therefore, the x-intercept is at 3, 0. I wanted you to see it graphically, but this is how you would find it algebraically. And if I just gave you that function without the graph, how would you know the intercept? This is how you would know it. Okay. Again, though, the y-intercept is still going to be none, because when the graph is shifted to the right like this, the asymptote is still going to keep it from ever reaching the y-axis. In fact, you may realize that the only way it's going to cross the y-axis is for that original graph to have been shifted to the left. So you would have to actually add something to the x inside the parentheses in order to actually have a y-intercept. The way it works out right now, if you plug in a 0 for the other variable, so if you plug in a 0 for x, we can say y equals log 0 minus 2. Okay, well, what does that mean? Y equals log of negative 2. Okay, what power of 10 is going to give me negative 2? There isn't one. This part right here can't be negative, just like the base can't be negative. There's no power of 10 that's going to give me negative 2. So in that case, there is no y-intercept. There's the algebraic way of figuring that out. Okay, so in all the examples so far, we've been using log base 10, and it doesn't make that big of a difference. It does make it a little easier in the sense that you can type it into your calculator. You can just type log, and it does the base 10 in the calculator. So I want to do an example with a different base. This is log base 2, and your first homework sheet's going to have log base 2, so this will be a good example to look at. We'll see how this affects things. Now, like before, the plus 2 is going to shift it to the left, which means it will cross the y-axis, which means there will be a y-intercept. Okay, so let's just see how some of these things work out. What's going to make the part on the inside equal 0? That's our asymptote and our domain. It's going to be negative 2 in this case. So the asymptote is x equals negative 2. And since the domain is going to go to the right from there, let's do a little sketch of it. It's going to go kind of like this somehow. It's going to somehow go like that. It's going to have to cross over at some point, right? Since it goes left and right forever, we're going to say it's from negative 2 to infinity, or x has to be greater than negative 2. Okay, and this is a very rough sketch. I'm just kind of getting the direction. So let's see where the intercepts are. So for the x-intercept, I need to plug in a 0 for the other variable, which means I need to set it equal to 0. And now I got to solve that. So I'll add 1. Okay, now I've just got the logarithm by itself, so I'm going to rewrite the logarithm as an exponent. I'm going to say 2 to the first equals x plus 2. Well, 2 to the first is 2, so I'm going to subtract 2 from both sides. I see x equals 0. Hey, well, it turns out my schedule is actually pretty close, and that was not on purpose. If the x-intercept is 0, 0, there's a trick. You may realize that if it crosses at 0, 0, that means it's crossing both axes. That means the y-intercept must also be 0, 0. Let's pretend for a minute that we didn't know that, just so we can practice the process. But if you see the x-intercept is 0, 0, that means that's the y-intercept also. That's always the case. All right, so for the y-intercept, we're going to plug in 0 for x. So I'm going to say y equals log base 2 of 0 plus 2 minus 1. Okay, so y equals, now what power of 2 gives me 2? This one you can actually calculate just using some reasoning. What power of 2 gives me 2? The answer is 1 minus 1, which is 0. So that one also worked out very nicely. Okay, and one last example, and I would encourage you to pause the video at this point and see if you can solve the problem. Okay, so now I'm going to go ahead and solve it. So the domain and asymptote, remember that's what's going to make the part inside equal to 0. So if I set 3x plus 1 equal to 0, my answer is going to be negative 1/3. So the asymptote will be x equals negative 1/3, and the domain is x is greater than negative 1/3. Greater than because, as usual, the x term is not negative. It would take a negative sign here to flip that to a less than, and it would make the graph go this way. Okay, so then for the intercepts, again, for the x-intercept, set y equal to 0. So the whole thing is equal to 0. F of x is y. Okay, 0 equals log base 2 of 3x plus 1 minus 3. I'm going to add the 3 to the side first. Now I've got the log by itself, so I'm going to rewrite it as an exponent. So 2 to the third equals 3x plus 1. 2 to the third is just 8. I can subtract 1 from both sides, so 7 equals 3x. That means x equals 7 divided by 3, or 7/3. And I'm just going to leave it as a fraction. You could write it as a decimal if you want to, 2.3 repeating. But that means this is going to be 7/3, 0. Or again, you could write 2.333 for this. All right, and for the y-intercept, plug in a 0 for x. So y equals log base 2, 3 times, parentheses, 0, plus 1, minus 3. Well, this part's just going to be 0. So we get log base 2 of 1 minus 3. What power of 2 will give me 1? What power of 2 will give me 1? The answer is 0. 2 to the 0 power is 1, because anything to the 0 power is 1. So if 2 to the 0 power is 1, then log base 2 of 1 is 0 minus 3. 2 to the 0 power is 1. And 0 minus 3 is negative 3. So then my y-intercept is 0, negative 3.